Okay, we're going to open up the second quarter talking about chemical bonding. And in this process, we'll be talking for a couple of weeks about this. And we will include some ideas regarding the geometry of molecules. We may get to that a little bit this week, and for sure next week we will talk about that. So first of all, we have to go over the types of chemical bonds. A chemical bond is an attractive force that occurs between atoms that's strong enough to enable the group to act as a single entity or a single unit. Now this is to distinguish a chemical bond from something we will talk about in the future called intra or intermolecular forces and intramolecular forces. These forces also are attractive and cause certain things to happen, but they are not strong enough to keep the groups of atoms together as a unit the way a chemical bond keeps the atoms together. Chemical bonding is extremely important because it determines the physical aspects of the matter that is composed, as well as the shapes and properties of the component units of the matter. So the chemical bonding that occurs determines the properties of the molecules that are formed in the compound. Molecular shapes are important because they determine the types of bonding that or forces that occur between molecules. Intermolecular means between inter means between the molecules. And so the various shapes help to determine what sorts of forces are present and how strong they are. The valence electrons are critical in determining the type of chemical bond that will occur. Now you'll recall that the valence electron is the electrons that are in the outermost shell of the atom, and they are the ones that interact with other atoms and form chemical bonds. The groups on the periodic table are important because the group number is the same as the number of valence electrons, and thus that's why the atoms in the same group have similar chemical and physical properties. So for example, excluding the transitional elements, which are in the middle of the table, if you start on the left, a 1A element, which includes excluding hydrogen, so starting with sodium and potassium and so forth, all of those have one valence electron. Now hydrogen also has one valence electron, but it does not follow the properties the same as the rest of the 1A elements. In the 2A group, you start with magnesium and then calcium, and on down that group, each of those atoms has two valence electrons. Now if you skip through the transitional elements, you come to the 3A group. The 3A group is headed by aluminum, which has three valence electrons. Actually, it might be headed by beryllium. My memory is failing me here right now. And then the 4A group, which is headed by carbon and silicon, has four valence electrons. The 5A group is headed by nitrogen and phosphorus. It has five valence electrons. The 6A group is oxygen and sulfur, has six valence electrons. And the 7A group are the halogens, fluorine, chlorine, bromine, and iodine. They all have seven valence electrons. And then lastly, the noble gases have eight valence electrons, starting with helium and neon. Now, the thing about the noble gases is because they have eight valence electrons, they actually don't interact with other atoms. And for this reason, they're called noble gases. Now, as the rule of octet states that elements will react with each other, and their purpose in interacting is to achieve 8 electrons in their outer shell, and they do this by either swiping electrons from other atoms, and the other atoms give them up freely because underneath that atom ion or that electron is a group of 8 electrons, or they share electrons. And these are the different kinds of bondings that can occur. As I said, the rule of octet is achieved by either gaining electrons, losing electrons, or sharing electrons. Now, the first type of chemical bond that we'll talk about is the ionic bond. The ionic bond occurs where electrons from one atom are totally given away by that atom to another atom, which takes them freely, and at the end each atom has 8 electrons in its outer shell. The result is a positively charged ion called a cation and negatively charged ions called anions. This type of bond occurs when there's significant difference in electronegativity between the atoms. Now, the electronegativity of an atom is its desire to hold on to its electrons. So, for example, sodium and potassium in the 1A group have a single electron out there in its outermost shell. It has a very low electronegativity, which means it's very much willing to give up that electron, exposing the lower shell, which has 8 electrons. On the other hand, if you go over to the 7A group, fluorine, chlorine, bromine, these have 7 valence electrons, and they very much want to keep those, and their electronegativity is quite high. And so they will grab an electron in order to fulfill their shell. The ionic bonding usually occurs with a metal, which is on the left side of the periodic table and has a lower electronegativity, with a nonmetal, which is on the right side of the periodic table and has a higher electronegativity. So here's an example. This is sodium chloride, which is table salt. And what you can see here is that the sodium atom has given up an electron to become a sodium ion, positively charged, so it's a cation. At the same time, the chlorine atom has gained an electron, becoming the chlorine ion, or the cation or anion. In the process of this occurring, each of these has charges which are attractive to each other. And so they tend to build a lattice structure as shown in A and B here, so that each sodium is surrounded by chlorines and each chlorine is surrounded by sodiums, and you end up with a lattice that looks somewhat like a square or a block. Now, with ionic bonds, you start out with 2 atoms, one of which, the sodium, has a very low electronegativity and is very desirous to give up that electrons to expose the 8 electrons that are underneath that single electron, fulfilling the rule of octet for it. And then the chlorine takes that electron and fills its shell with 8 electrons. And so you end up with a positive sodium and a negative chlorine. The positive sodium is called a cation, the negative chlorine is called an anion. Now, what generally occurs is you look at the periodic table and remember that the left side of the table is mostly lower electronegativity, which unfortunately is called positivity in this, which I think is confusing. But just think of the left side of the table as the metals group, and the metals group have lower electronegativity. The right side of the table, on the other hand, is the nonmetals group and has a high electronegativity. And so when you have a large separation, as shown with the RBF in the middle of the diagram, you have a large separation, you form ionic bonds. Now, what this is going to also shows, and we will look at this in just a second, when you have two elements that are close together, like carbon and oxygen, they have fairly similar electronegativities, and they tend to form covalent bonds. Hydrogen is a unique situation where it's on the left side of the periodic table and it has one electron, but it does not act as a metal. It acts as a nonmetal, and so it binds like a nonmetal. The properties of ionic bonds are shown in this slide. They tend to form crystalline solids at room temperature with very high melting points and boiling points. So the intramolecular forces that occur are fairly strong, and they're ionic forces that drive this into a solid structure that's difficult to break apart. When they are molten, they conduct electricity quite well because the ions are free to move. When they're in their solid state, they're fixed, and so they actually do not conduct electricity well. Most are soluble in water, and water is what's known as a polar solvent, which I will talk about what that means in just a few minutes. But most of these are soluble in water and not soluble in other types of solvents. Solutions of these ionic compounds tend to conduct electricity because what happens is the lattice structure is broken apart by the solvent, which is water, and then the ions float freely and can transfer electrons through the solution. Pure water does not conduct electricity well. And as I said before, the crystalline solids don't conduct electricity well. But when you break the solid down with the water and release the ions, then electricity or electrons can move through the fluid. And as I said, other types of solvents like benzene and oil and alcohol are less polar, and therefore the ionic substances are not necessarily soluble in these nonpolar solvents. Now, covalent bonds occur when the two or more atoms actually share electrons. So with the ionic bond, remember there was a transfer that was somewhat semi-permanent. In this case, there's a sharing agreement that occurs, and each sharing leads to 8 electrons in the particular atom that goes along with the sharing. Electrons are shared in pairs. The sharing may be equal, in which case the bond is nonpolar, or sometimes one of the two atoms holds on to the electrons longer than the other one, and the sharing is not equal, and that's called a polar covalent bond. There's similar electronegativities between the two atoms, and it's usually two nonmetals that are combining together. So here's an example of a covalent bond between hydrogen and chlorine, and this one is a polar covalent bond. And the reason for that is that the electronegativity for chlorine is higher than the electronegativity for hydrogen. And so the electron spends more time around the chlorine, the pair of electrons spend more time around the chlorine than around the hydrogen, which is designated by the darker green cloud around the chlorine and the lighter green cloud around the hydrogen. And this can be designated as it is in diagram A with an arrow and a crosshatch. The arrowhead represents where the electrons spend most of their time, and the crosshatch represents where they spend less time. It can also be shown as in diagram B with lowercase Greek deltas, delta plus being the positive side, therefore less electron time, and delta minus being the negative side. Electronegativity values were derived by Pauling and follow this predictive periodic trend with higher electronegativities seen as you go to the right of the periodic table and toward the top of the periodic table. So you can see, for example, if you look at fluorine, it's all the way on the right and all the way on the top, so it has the highest electronegativity. But even in that group, as you go down, you'll notice the electronegativity decreases as you go down the group 7A. Similarly, if you look on the left side of the table with lithium, sodium, potassium, you see that the electronegativity goes down as you move down that column. But as you go across from left to right, you see that the electronegativity goes up on any particular row.